Okay. And we're going to go. So again, just as an announcement to make sure everyone knows about this, the review for the first test is posted and the solutions are posted. I waited a while to post the solutions because I didn't want you guys relying on that as a crutch. So there's good reason to follow the guideline as I laid them out, so that you kind of know what you know, I guess, is the best way you want to put it. So you do want, I listed the topics that I care about, and then I said study these and then try the review under test conditions, and then go back over your work on your own, go back over your work with group members, and then you can check the solutions after, maybe after redoing the test once more in a shorter amount of time. So one thing you don't really want to do at this point is to do something like go back and study from your homework or rereading all your notes, because that will take a lot of time. It's not very efficient time-wise. And if you actually did the homework properly the first time, don't worry about it. You already got the benefits from that. But the homework was kind of all over the place, and it's kind of giving you a well-rounded knowledge, but I'll be testing on specific skills that I want to see. And so you're really going to want to use the review as a guide. And the reason why you're going to want to do it under timed conditions is because, one, you should know roughly how quickly I want you to be able to do certain things, but also it kind of encourages you to make mistakes that you wouldn't otherwise make if you're literally taking forever to do something. You'll have, if you take forever to do it, you'll get a better perception of your skills than if you actually do it in a short amount of time, like when you're under pressure. And it's also, with a lot of things, hindsight is 20/20. So if you check the solutions before actually trying it on your own, a lot of things in the solutions might look, yeah, that was obvious, and you'll feel like, oh, I understand what I'm doing. But at the end of the day, if you didn't have the solutions and you had to come up with that, it's kind of a different story usually. Sometimes you can watch me do something on the board and it's like, oh yeah, that makes sense. But if you had to come up with that from scratch, it's not as easy as you might think. So if you go to the solutions first, there's that kind of thing. It'll trick you into thinking you understand more than you actually do understand. So it's very important that you actually practice it under time conditions, pretend it's a test, and that will actually tell you what you know versus what you don't know. The test that's online, it's sort of written so that you take an average of 15 minutes on each problem, whereas in our actual test, you'll have about 10 minutes for each problem, so the test will be slightly shorter. But it's still, if you know you should be spending roughly 15 minutes on a problem, but you're spending 20, that kind of indicates to you maybe I'm kind of shaky on this. You know what I mean? So it's good to actually time yourself and really practice based on the test. So I'm not going to care that you know literally everything we've spoken about, but there are some specific things I need you to know. I need you to know how to simplify things. I need you to know how to draw graphs. I need you to know how to develop equations from word problems. I need to know how to figure out the equation of a line. Things like that you'll see in the review. So you'll know exactly what I expect you to know at this point. So that's important. And doing it as a test will tell you what you do know from what you don't, as opposed to doing it in some other way. So that's that. So make sure you go over that. And again, on Monday, I have my office hours here for a few hours. So you guys can talk to me on Monday if anything. So we're going to continue with 2.2. We started talking about limits. Let's recap. We did like many different examples, but to recap some essential knowledge that we're talking about here. What I want you to think of when you're thinking of limits. Limit as x approaches a of f of x. How I want you to think of this is this as the y value f approaches as x approaches a, right? So remember, limits, one of the things we do, one of the concepts that is essential to a limit is that we don't actually care about being at this point, we care about getting close to that point. And then we care about watching what is the y value doing. So the y value is the important thing when you're talking about limits. What is the output of the function doing when my input is getting close to a certain value? That's a very important thing. So that's one thing you wanted to know about limits. So basically, the important idea is watch the y value And it should be a case where there's the y value. If there's a case where there's several y values, the limit doesn't exist. Okay? And you just want to get close. You don't actually care if you can be there or not. Okay? And we also spoke about infinite limits and limits at infinity. So let's actually jump back into that discussion. I think I wrote these down, but I want to go over them slowly again. Let's look at each of these. Like limit as x approaches 0 from the right of 1 over x. Limit as x approaches 0 from the left of 1 over x. Limit as x approaches 0 of 1 over x. Let's also look at limit as x approaches 0 from the right of 1 over x squared. Just x approaches 0. Let's look at all these guys. So what do you think about part A? Yeah?
It's gonna look like the curve coming, like the closer it gets to 0, it's gonna go up.
Okay, so you kind of know what this looks like, right? So I see your hand waving the thing. Do you know what it looks like on this side?
It's like reflected over the origin.
It's reflected there, right? It's actually an odd function, by the way. So yes, you do reflect over the origin. So that's kind of what it looks like. So now you're looking at 0, and you're thinking about approaching 0 from the right side, which means you're a little positive, you're a little bigger than 0, and you're coming down this way. And you can notice as your x values are inching closer and closer to 0, what's your y values? It goes here, then it goes here, then it goes here, then it goes here. The y values keep getting larger and larger the closer you get to 0, right? And the limit is about what is the y value doing. Okay? So one way you can look at A is from the graph. Right? Knowing the graph of this function actually can help you talk about the limit as x approaches 0 from the right. Another thing you could have done is a table of values where you could actually just plug in values and see what's happening. Now at 0, you can't actually get an output. This is x and this is 1 over x. You don't actually get an output when you plug in 0, of course. But you can inch closer to 0, like 1/10, 1/100. 1/1000th, 1/1,000,000th, right? And what has happened if you take 1 over 10? Well, that becomes 10. The output here would be 100. The output here would be 1,000. The output here would be 1,000,000. What you notice happens to the y values is they're all just getting bigger and bigger and bigger. So you can plug in a bunch of test values and track what the y value is doing. It seems to get bigger and bigger and bigger. It's going off to infinity. Okay. Now, in a case like this, like 1 over x or something like 1 over x squared, the graph is the recommended way to do it. Because it's going to be very quickly, like you got to the answer pretty quickly by thinking of the picture. Oh, the graph goes like this, so the y values go up, right? As opposed to you coming up with numbers and plugging into the formula and calculating them. You know, it's a doable thing. But it tends to be, if you do know the graph of the thing that you're looking at, that's a much quicker way to get to what the answer would be. And just recognizing that the limit is really tracking the y values, knowing what's happening to the function is going to help you come away with that knowledge. So at the end of the day, what this means is that the limit as x approaches 0 from the right of 1 over x is positive infinity. That's positive infinity. In a similar way, we can figure out what is the limit as x approaches 0 from the left. So we can look at b, and we can look at the limit as x approaches 0 from the left side of 1 over x. So again, we can look at what the picture looks like. On this side is where we're approaching 0 from the left. What is happening to all the y values? The graph keeps going down and down and down. So this guy seems to be approaching negative infinity. And so that's what we could get here, negative infinity. Right, just by looking at the y values, what they're doing. What's that limit? Limit as x approaches 0.
Does not exist.
Oh, were you raising your hand to answer this, or was there another question? Okay, yeah. That guy, based on what we do know about limits, there should be the y value. There should be a unique answer that agrees from both sides. On this side, we see we're getting a positive infinity. From the other side, we're getting negative infinity. They're both infinite, but they're infinite in the opposite direction. They disagree, because here I'm getting negative values, over there I'm getting positive values. And so here we would say it does not exist, we write D in it. What about the 1 over x squared?
Infinities.
Limit as x approaches 0 of 1 over x squared. So limit as x approaches 0 of 1 over x did not exist. What do you think about 1 over x?
Positive infinity.
Why?
Because since it's squared, when you're approaching from the left, the negatives cancel out, so we both go to infinity.
Right. And another way we can think about that as also is the graph of 1 over x squared. We should know by this point. It makes all this positive and it increases the steepness of how they're moving. So that's that graph. So in this case, if we're approaching 0 from the right side, our y value is getting bigger and bigger and bigger. And if we're approaching 0 from the left side, our y value is also getting bigger and bigger and bigger. Both sides are agreeing. This means that our limit as x approaches 0 of 1 over x squared is infinity. And that would be your answer. Now, technically speaking, infinity is not a number, but it is something that can talk about the behavior of the function, and a lot of times that's what we care about. How is the function behaving? So while this is not a number, it does give us an idea of what the function is doing. It just keeps getting bigger and bigger and bigger. Right? And there are going to be many cases in which knowing the behavior of the function is going to be an important thing to figure out. So here's one thing well, maybe I'll tell you. Yeah, I'll give you the strategy at this point. You might have noticed our very first example when we did a limit, we kind of had different approaches up until this point. You might remember our first example was limit as x approaches 1 of x plus 1, and then we looked at something like limit as x approaches 1 of x squared minus 1 over x minus 1. And then just now we looked at the limit as x approaches 0 of 1 over x. And you may have noticed that our approach kind of changes based on what we're looking at. So for this one, this function was very nice. It was just a straight line. We just graph that and figure out what the y value was approaching, right? So what we did was we could literally just plug in x equals 1. There was like nothing wrong with doing that here, and that as close as you can get to as x approaches 1, the closest you can get is to actually be 1. Not always something that's required for a limit, but in this case we could do that, so we just did that. In this case, though, we couldn't plug in 1 because we divide by 0, but the trick was here to simplify. It turns out you could simplify this guy as x minus 1 times x plus 1. And as long as we're not at x equals 1, we're not dividing by 0, this is just a fraction that we can reduce. And so that actually ends up giving us the same answer as that limit. So while the function doesn't exist and I couldn't plug in a number, the limit does exist. Now you look at something like this one and you realize that neither of the first two approaches work. Like I can't plug in x equals 0. I also can't simplify to cancel the fact that I would have to plug in x equals 0, the denominator. So I can't plug in the number, I can't simplify to get the number. So what did I look at here? I figured out that this does not exist, but I didn't figure it out by doing one of these approaches. I just actually looked at the graph. Right? So here what we did was we plugged in. Here's what we did first is we simplified, then plugged in. Here's, we actually use the graph, or even knowing about the behavior of the function. Right? And I did these examples in this particular order because it's kind of the order in which I want you to approach all these limit problems. So in general, if I give you a limit to figure out, like on a test or a quiz or on whatever else, I'm not going to tell you the approach that you should take. I'm not going to tell you, oh, you should probably do a table of values here, or oh, you should probably think about simplifying. I'm just going to give you a limit and you have to figure out the best way to compute it. And so that might seem daunting. So to have some solid footing here, I can actually give you guys a strategy for approaching limits. What you want to do first, what you want to do second, what you want to do third, how you want to think about applying the principles that you're learning here. Right? So this is to compute limit as x approaches a of f of x. Right? So I give you a random limit problem, and I say find the limit of this function as x approaches a. It turns out the first thing you'll always try to do when seeing any such problem is try to plug in x equals a. That's what we did in this case, the easiest case. It's also going to be the one where, if it works, it's going to be the easiest one to get to. You literally just plug in the number and calculate it. And as long as you're not dividing by 0, or there's not a negative under a radical, or there's not all these things that we know are bad, it's fine to just plug in the number. The y value is your limit. Right? That is always the first thing you're going to want to do. So I give you a random limit problem. The first thing you're going to try to do is see, can I plug in that x value? If you can, just do it. Okay? If you can't, then you move on to step 2. So I give you a random limit problem. The first thing you're going to try to do is plug in the x value. Suppose we can't plug in the x value. So for example, like here, I couldn't actually plug in x equals 1. The next step is to simplify, or I shouldn't, to simplify it doesn't always work. So let me say, try to simplify. Try to simplify so you can plug in x equals 8. The output after doing that is the limit. So you can do that. So that strategy actually worked here. So I saw this limit. Probably the first thing I would try to do is, can I plug in x equals 1? The immediate answer should be no, because you get divided by 0. So then you think, can I simplify so that I can plug in 1? So you decide to simplify a fraction. The way you simplify a fraction is you factor the top and the bottom, and then you cancel common terms. Right? So in this case it's simplified, and I was left over with something where I could plug in 1, and so that's how I would deal with this one. Right? So that's where step 2 would come in. And step 2 is okay to actually kill that guy. If you can't do that, that brings us to step 3 in your strategy, which is the strategy that we have to do here. Notice for this guy, I couldn't plug in x equals 0. I can't simplify to be able to plug in x equals 0. So what did I fall back on? The graph, or a table of values. And like I said, the graph is kind of the recommended way. More often than not, you're going to want to kind of look at the graph. So it's recommended that you sort of look at this first. Because finding the table of values is really annoying. Right? And that's what worked out with our examples like limit as x approaches 0 for 1 over x, or limit as x approaches 0 for 1 over x. And if you look at, well, not to spoil it for you, but if you look at even the bonus problems on the quizzes, you're going to see me using this idea here. Another thing, so there are times when I might give you something that's slightly complicated, where the graphs of the function, even though in theory it would be a good way to figure it out, it's kind of difficult to do that. If graph is difficult. This brings you to a fourth option. Here is to apply your knowledge of how different functions relate to each other. And there are going to be several kinds of relationships here that we can talk about. But at this point, this is the basic strategy that we will have for limits up to this point. We'll look at several applications of step 4, but one application of step 4 is to limits at infinity. Right? And there are some ways you can talk about the different kinds of functions that we've spoken about. So as x is getting closer to infinity, let's say our a is greater than 1, the following relationships will always hold. Right? So this is one application of step 4, talking about the relationship between different functions. We spoke about log functions, log to the base a of x. It turns out as x is going to infinity, such a function will always be much less, this is like much less, emphasis on the word much, less than a polynomial, right? Or you can even put this as x here, whatever. Right? Now when I say much less, I do mean really much less, meaning as your x is going to infinity, if you're comparing a function that looks like this to a function that looks like that, this guy is going to be so huge in relation to this guy, it's going to be as if this guy's nothing, like he might as well be 0, right? And it doesn't even matter what base you're comparing it to. Polynomials are always bigger at infinity than log functions, right? When a polynomial, when your x starts getting huge, the outputs of this guy is going to be vastly bigger than the outputs of this guy. Right? So this guy's like 0 compared to that guy when you're off to infinity. Right? Now that relationship is going to be important when you're doing limits at infinity. It turns out that polynomials are also vastly smaller than exponential functions. So if I'm comparing something like e to the x to any polynomial, e to the x will win as you're going off to infinity. Right? Your e to the x is going to be so huge when your x is going off to infinity, like x to any power is not going to matter. It doesn't matter if I have x to the 1,000,000th power. E to the x will eventually be a lot bigger than that guy, to the point where this guy's like nothing. Okay? There's some other relationships here, like x factorial and x raised to the x, but we're not really going to look at functions like this in this class. But at least these three you guys should really know about. Exponentials are always bigger than polynomials, and polynomials are always bigger than logarithms as your x is approaching infinity. So how can you use this to your advantage? Let's say I give you an example like this. So this is an example when knowing the relationship between functions is going to be beneficial to you. So let's say I'm taking the limit as x approaches infinity of x to the 10th divided by e to the x. So let's say you have a limit like that. Now you might start to run through your limit strategy, and you should. What you're going to want to do is can you figure out the answer by plugging in your x values? Let's say I plug in x is infinity in the top and the bottom. I really get an infinite number divided by an infinite number, and that could literally be anything. That's not actually going to be an answer. That's something we call an indeterminate form. So you can't figure that out by plugging in. What does it even mean to plug in infinity anyway? So the plugging in answer won't work. Then you try to think, can I simplify that to be able to plug in an answer and somehow get sense out of it? And that won't work either, because how am I going to simplify x to the 10 and e to the x? Nothing there really cancels or anything like that. So then I might go to the third option. What would the graph of this look like? Well, the graph of x to the 10 you would know, the graph of e to the x you would know, but the graph of this divided by that is not a graph that you would know. And it's actually pretty complicated to actually figure out what that graph looks like. We're going to do a topic called curve sketching in this class, but even with all the knowledge that we'll get by studying that, graphing this guy is still going to be very annoying. So the graph is probably not what we want to look at either. But then now knowing about how these functions relate to each other, and I realize that e to the x is going to be huge compared to x to any power, that kind of gives me a way to figure this out. Because now what I can see, when I look at this fraction, what I'm seeing now is there's something small divided by something huge. And what kind of number does that go to? If you have a fraction where the numerator is a small number and the denominator is a big number,
0.
it would all approach 0. This means this is approaching 0. If you have a fraction and your denominator keeps getting larger and larger and larger while your numerator is staying small, the fraction keeps getting smaller and smaller and smaller. Right? Think of 1 over 10 versus 1 over 100 versus 1 over 1,000 versus 1 over a million. These are progressively getting smaller when the denominator is getting larger. So as your denominator gets large in a fraction, the overall fraction gets very small. And so because I know how an exponential and a polynomial relates to each other, exponentials are huge compared to polynomials when you're at infinity. This fraction I can see, oh, that's just a small number or a huge number. The answer should be 0. And of course, like vice versa, if I had this guy, my e to the x was divided by x to the 10th, then I'd realize, oh, this is a huge number divided into a small number. You still have a huge number of pieces. This will give you infinity. Right, by the same kind of flipping that relationship. Right, if you know that the numerator of a fraction is larger, the overall fraction is larger. Right, so this is kind of how you're going to want to approach limit problems. One, you try to plug in a number. If that doesn't work, try to simplify so you can plug in a number. If that doesn't work, use what you know about the graph or maybe a table of values. If that doesn't work, use what you know about the nature of the functions themselves and how they relate to each other. And oftentimes that will give you a good way to figure out what the answer is. And of course, these rules only work at infinity. You would know this for sure. But if we weren't at infinity, you can almost just use one of the previous rules to work. So I mean, if we did something like limit as x approaches 1 of x to the 10 over e to the x, then step 1 actually works here. Right? I could literally just plug 1 in. So that limit is just 1 over e. Step 1 would work on something like that. But if you're going to like infinity, then the rule I mentioned applies. So these are just different strategies for limits, and it's kind of how you can use this to approach any of the limit problems. Right? And you'd want to approach it in that order, because I think it's easiest to do these problems in that order. So you check to see, can I plug in a number and get an answer? If not, can I simplify to be able to plug in that number and get an answer? If not, what can I know about the graph? If not, what do I know about the nature of the functions themselves? And this is one relationship in which we know about. As x is going off to infinity, these different functions relate to each other in these different ways. There's also a relationship of how polynomials relate to each other. Also, as x approaches infinity, then if you have x to the n, will be much less than x to the n if your m is bigger than n. Right? It turns out that that's always true. So even if you have polynomials like x squared versus x cubed, at infinity your x cubed would be huge compared to your x squared. So even polynomials, by changing the degrees, how these functions relate to each other is actually quite significant. This guy will get so huge that that guy's like nothing once his power is bigger. So if you had something like, for example, this would mean, for example, if I take the limit of x squared divided by x cubed as x is going to infinity, I would know that that answer is 0. Silly example, because you could also realize that you could have simplified here, you get 1 over x, and then that makes sense. Or the other way, if I had x cubed over x squared, this guy's bigger, so that's going to infinity. Right, so you can look at that. Right? And yes, of course, here you could have simplified, but there are cases where you can't just simplify like that. I'll go into this kind of more in detail later, but for now I actually just want to give you some properties of limits that you can apply to find more complicated limits. So let's do that. So how about the limit laws? Let's see a constant, and suppose the limit as x approaches a of f of x, and the limit as x approaches a of g of x exist and are finite. Then the following hold. 1. And here I'm going to tell you about the properties of limits essentially. The limit of a constant times a function is equal to the constant times the limit of the function. In other words, when you're taking limits, constants are something you can always factor out. And you will get the same answer. So this is basically saying something like the limit, for example, the limit as x approaches 1 of 2x plus 2 is actually the same as just me factoring out that common 2 and look at the limit as x approaches 1 of x plus 1. Right, these two limits will give you the same answer. In fact, they will give you the answer 4. Right, knowing that this and this will give the same answers might come in handy. Right, you can always factor out common factors. You can factor constants and put them outside of them. To prove these, you really need the precise definition of a limit, and we kind of did a fuzzy definition. So at the moment, you just kind of have to take my word for all these. But one other thing that you want to know about limits is that they actually distribute across sums and across sums. So if you want the limit of f of x plus or minus g of x, that is equal to the limit of f plus or minus the limit of g of x. So if you're adding two things together, you could choose to split them up into two separate parts and figure out the limits for each part separately and add those answers together, and it will be the same thing. Right, so limits distribute across sums. So me finding something like the limit as x approaches 1 of x squared plus e to the x, that's the same as me finding the limit as x approaches 1 of x squared plus the limit as x approaches 1 of e to the x. Like I can do these separately. That would of course be 1 and 2. Of course you could also do it like a direct plug-in. Right, if you follow the strategy I gave you earlier, you probably don't even have to think about it this way, but you could think about it that way for more complicated cases, where you just might want to split things up and deal with one case at a time. You can do that with limits. They will distribute across sums and products. Here's a weird property, but it works with limits. A limit will distribute to each part of a product. So notice that the distributive law does not work this way, but limits actually work this way. Like if you have a limit of a product, you can actually take the limit of this part and multiply it by the limit of the other part. right? So limits kind of distribute across products. Notice that the distributive law does not work that way, but limits do. So that's something that you might be able to take advantage of. So for example, if you have the limit as x approaches 1 of x times e to the x, you could realize that this is the limit as x approaches 1 of x times the limit as x approaches 1 of e to the x. So this guy would give you 1, that guy would give you e, so the answer in this case is e. You could also recognize that if you followed the strategy I gave you earlier, a direct plug-in would actually take you straight to there anyway. But if there's some case where separating the product would be easier for you, you have that option, you can do that, and it's legal. Of course, division is simply multiplication by the reciprocal, so whatever works for multiplication will also work for division. So that's the fourth, whenever division is possible. That's the fourth rule. Limit of a division of functions you can think of as the limit of the top divided by the limit of the bottom. As long as your limit of the bottom is not 0, of course. So, as x approaches 1 of x over e to the x, you can think of this as the limit as x approaches 1 of x over the limit as x approaches 1 of e to the x, which is 1 over e. Yes?
What types of situations though would you do this? Why do you want to do these things?
It'll come in handy later when we're doing things like derivatives. Knowing these properties can help us prove a lot of things and derive a lot of important things. But in terms of, so it's important to know these rules and when you can and cannot do something. Also, but knowing the strategies that I gave you before on your average limit problem, it'll work out even if you don't think in terms of this way. But there are situations where it's beneficial to think in terms of this way. Right, and knowing these just might help you employ the strategy that I gave you earlier more efficiently. Another thing you can know about limits is that they pass through powers. So if you have the limit as x approaches a of some function and it's raised to a power, you can find the limit of the inside and then take the power afterwards. As long as your power is positive. If your power is negative, then you have to worry about dividing by 0, but a similar thing can hold true. Right, so if I have something like the limit as x approaches 2 of x plus 1 cubed, that's the same as me looking at the limit as x approaches 2 of x plus 1 and then cubing that answer. So I can get 3, and then I cube that answer, and get 27. Yeah. So those give us the properties. I want to talk about continuity, but I don't know if I can finish that in time. Maybe we can do some other examples. talk about limits of it at infinity at rational functions. I can probably get through that. Okay, so remember a rational function is just a ratio of polynomials. Let's do some examples to illustrate the rule. I'll tell you the rules right after I do these examples, but I just want you to see what's going on in the background. And then basically once you see this, you kind of never have to do it. You just know that this is going to be the rule, and I'll show you what you need to look for. So examples to illustrate. So let's say you have this example. Limit as x approaches infinity of something like x cubed plus something like that. Plugging in won't work, simplifying won't work, graphing won't work, but you do know the relationships of the functions in terms of their highest powers. Like a 5th degree power and a cubic power, this one is a lot bigger. So you can already see here, the denominator is huge compared to the numerator. Okay? But in terms of a rule that I want to give you, here's kind of how you could actually break this problem down. Is the strategy for ratios of polynomials when you're going off to infinity is to divide numerator and denominator by the highest power of x in the denominator. Right? You always divide by the highest powers of x in the denominator. Right? And that would leave you with the following. So we're going to take this and we're going to divide all the terms by x to the 5th. Right? We're going off to infinity, so we're not dividing by 0. We don't have to worry about that. I'm going to take this guy, x cubed, divide by x to the 5th, plus 4x divided by x to the 5th, minus 1 divided by x to the 5th, over 2x to the 5th divided by x to the 5th, minus 3x squared divided by x to the 5th, plus 7 divided by x to the 5th. So you'll do that. And you realize that this would go to the limit as x approaches infinity of this guy would be 1 over x squared, plus this guy would be 4 over x to the 4th. This guy would be 1 over x to the 5th. On the bottom, I would have 2 minus 3 over x cubed plus 7 over x to the 5th. And based on what we know about things like 1 over x squared, or 1 over x to the 4th, or 1 over x to the 5th, when you're going off to infinity, these guys, you realize they all go off to 0. So what I'm actually doing here is I'm applying a limit law. I'm looking at the limit of the top separately from the limit of the bottom. And if I look at the limit of this plus that, I can just look at the limit of each one. And I realize that each term in the top goes to 0. If I look at the bottom, each term here goes to 0. And I'm only left over with 2. So ultimately my answer is 0 divided by 2, or 0. But again, this is kind of a general rule. This will always happen if the power in the bottom is larger, because if I divide by the highest power of the denominator, I'll always get the constant of this guy, but everyone else will go to 0 because the denominators are all going to be bigger than the numerators. Okay? So I can write that down as a general rule, and I will summarize this as a general rule once we get to the end. Let's look at the other scenario. So here is when the highest power is in the denominator. Here's an example when the highest power is in the numerator. So let's say I have x to the 7 plus 3x cubed minus 4 over x cubed minus 7x plus 2. So you want to do something like that. Again, you divide by the highest power in the denominator. You always divide by the highest power in the denominator. That's never going to change. So I identify the highest power in the denominator. That's this guy. I'm going to divide everyone by x cubed. I'm going to take x to the 7 divided by x cubed plus 3x cubed divided by x cubed minus 4 divided by x cubed over x cubed divided by x cubed minus 7x divided by x cubed plus 2 divided by x cubed. And now I apply my limit property. Look at what all the tops are doing. So in the top, this guy would simplify to x to the 4th. And this guy would simplify just to 3. And this guy would simplify to 4 over x cubed. This will simplify to 1. That will simplify to 7 over x cubed, x squared. This guy would simplify to 2 over x cubed. As x is going to infinity, I know that these guys are going to 0, these guys are going to 0. And so I just basically have 1 in the denominator. Limit. And in the numerator, what do I have? This guy is going to 0, so I'm going to x to the 4th plus 3. So this guy just looks like x to the 4th plus 3, and obviously here, the bigger x gets, the bigger this gets. That's going off to infinity. And of course, something like that will always happen if the highest power is in the numerator, because if you divide by the biggest guy in the denominator, this guy is going to leave over a power of x that's going to get bigger and bigger and bigger. Right, so that something like that will always happen in this case. What if there's the same? The highest power in the numerator and the denominator are exactly the same numbers. Let's say we're doing this one. So something like 5x to the 6 minus 2x cubed plus 7x plus 3. And then I do something like 1 plus 2x squared minus 3x cubed minus 4x, something like that. So that guy shows up on a test. You realize that plugging in infinity doesn't really make any sense. Do you have a question?
No, I was going to answer.
Okay. Plugging in infinity doesn't really make any sense. And simplifying is not, like, to try to factor that, that's going to be too much. I wouldn't even try. The graph of that obviously is going to be very complicated. So now you're going to try to use the relationship between the functions, but you can again do what I asked you to do here. And you know what the answer is at the end of the day?
I think so.
What is it?
5 or negative 5 over 4.
It's going to be negative 5 over 4. Right? And we're going to see why that is. Because if we do the same strategy and divide the top and bottom by the highest power in the denominator, which here happens to be x to the 6. Here's what we get. We get 5x to the 6 divided by x to the 6. 2x cubed divided by x to the 6. 7x divided by x to the 6. 3 divided by x to the 6. 1 divided by x to the 6. 2x squared divided by x to the 6. 3x cubed divided by x to the 6. Minus 4x to the 6 divided by x to the 6. This will cancel, that will leave you with a 5 minus, this here will cancel, that will leave you with a 2 over x cubed. This cancel, that will leave you with a 7 over x to the 5th. This will leave you with a 6, 3 over x to the 6th. This will leave you with a 1 over x to the 6th plus a 2 over x to the 4th minus a 3 over x cubed minus 4. Again, I can apply the limit laws to the top and bottom separately. This guy's going to 0, that guy's going to 0, that guy's going to 0. This guy's going to 0, that guy's going to 0, this guy's going to 0. So at the end of the day, I basically have 5 minus 0 plus 0 plus 0 divided by 0 plus 0 minus 4, and the answer is minus 5 over 4. So as my x is going off to infinity, the y value of this function will actually go towards the number minus 5 over 4. Now you could prove this in general, right? This says, write a general polynomial where this is power n and that's power m, and you can do the 3 cases I just mentioned, but they'll always work out this way. And so that leads us to this general theory about the limit at infinity of rational functions. So this leads to the following. I'm going to limit as x approaches. It could be positive or negative infinity of p of x over q of x, where here p and q are polynomials. There are 3 possible situations you can find this in. There's one case where the power on the bottom is bigger than the power on the top. And in that case, the denominator will always overwhelm the numerator and you will get 0. So one possible answer for a problem like this is 0. And it will happen when so the answer to something like this will be 0 if the degree of q is bigger than the degree of p. Right, you guys understand this notation? But that means highest power. This means highest power. In other words, if the highest power is in the denominator, and you're going to, whether it's plus or minus infinity, the overall fraction will approach the number 0. There's another situation, plus or minus infinity. This is if the degree of p is greater than the degree of q. And in this case, you need to watch the signs. Right? Because whether it takes a plus or minus infinity depends on the coefficients and what you're going towards. So for example, so I'm looking at limit as x approaches infinity of something like x cubed plus 3 over, let's do this a little bigger. Okay, so 7 plus 3 over something like x squared minus 4 or something. Okay. So in this case, the top power is bigger. And so essentially what this theorem is kind of saying, that you only care about who the highest powers are, which means you identify the highest powers in your fraction, and you can literally ignore everyone else because they're going to either go to 0 or a number. Okay? So in terms of this, you realize that this guy's bigger than that, so this will cancel. And because your x is going to positive infinity, everything here is positive, right? And so you'll take the plus infinity. Contrast that with this limit. What if I had x goes to negative infinity? Of exactly the same thing. You can identify the highest powers. Notice that the highest power is bigger on the top. You can essentially ignore everyone else. But now there's a problem. Now your x is going to a negative number, and you have to worry about that. Because when you plug in a negative number and raise it to an odd power, what happens?
Stays negative.
It stays negative. Whereas in the denominator, here I'm squaring this negative number. So that the denominator is going to be positive. So I'm going to have a negative number divided by a positive number. So overall, while I know the answer should be infinity because the biggest one is on top, it will be negative infinity. Right, I have to pay attention to the signs and the powers that are in there. So you have to kind of be careful in this one. Right, so whether the power is odd or even, and whether your x is going to positive or negative infinity, you have to kind of watch the signs and make sure you're dividing if the signs will affect the outcome. So here you can have like a sign change happening, so you have to kind of be careful in that situation. But you do know that the answer will be some sort of infinity. You just have to pay attention to which one of the infinities. Okay. So that's the second case. You can have where the denominator has a higher power than the numerator, you will always get 0. If the numerator has a higher power than the denominator, you will always be infinite. You just have to be careful which infinity, right? By watching the signs and how the powers work out. And then there's one third case. So this is called the ratio of the leading coefficients case. So this would be the leading coefficient of P divided by the leading coefficient of Q. And that's if their powers are actually the same. If the degree of P is exactly the same as the degree of Q, you take what's called the ratio of leading coefficients. So let's say I have its limit as x approaches infinity. So you see a problem like that, you realize your x is going to infinity, because otherwise this theorem doesn't apply. It has to be going to infinity. So what you do is you look for the highest powers in the top and the bottom. Notice that it's those two guys. Notice that the highest powers are the same. The answer is going to be therefore 7 over 3. And you don't have to do anything else. It also doesn't matter if this was a negative infinity. It would still be 7 over 3, whether it's plus or minus. Because if this were negative, since they're both odd, they both will factor out the negatives and they'll cancel each other. So the sign is actually not going to matter. Because once they're the same powers, if they're both even, the answer is not going to matter anyway because you're raising a negative number to an even power. But even if they're both odd, they'll both factor out a negative at the same time, and so it'll end up being positive anyway. So the sign is not going to matter whether you're going to positive or negative infinity. So literally if they're the same powers in the top and bottom, the highest powers are the same, you simply take the coefficient of the top guy, divide by the coefficient of the bottom guy. Do another example here. Talk about this one. Limit. That over so you see a limit like that on a problem. What's the answer?
-15 over 2.
Minus 15 over 2. It's not going to be a big deal, right? So you see this. Once you see x going to infinity of a rational function, your first thing to do is to identify the highest powers. Highest power on the top is that guy. Highest power on the bottom is that guy. They happen to be the same. They're both x to the 9th. So you just take the coefficients. Minus 15 over 2. And you don't actually have to do anything. It's one of those things that you can take at a glance. We're still not done with limits. There are other cases we're going to want to cover, as well as continuity, but we can stop there for now. I think we even covered everything that you need for the bonus on this test. Let's see how that goes.